Sebagai dedikasinya terhadap lingkungan, Institut Teknologi Kalimantan membuka teknik lingkungan yang mempelajari semua penyebab permasalahan di lingkungan, mulai limbah padat atau sampah, bahan berbahaya dan beracun, B3, hingga limbah laut. Sebagai wadah pengembangan diri mahasiswa, Institut Teknologi Kalimantan menyediakan unit kegiatan mahasiswa diantaranya Asma Warman, Rik M. Enggang, Futsal, Basket, Tenis, Voli, Badminton, Seni Budaya, Kopma, Fokus Point, ITK Musik, Paduan Suara Mahasiswa ITK, Volks, Pramuka, Gangga Yaksa, Developer Student Club, Spekta untuk Sang Pencipta, dan Bumi Atom.
Assalamualaikum warahmatullahi wabarakatuh. Perkenalkan, saya Yunita Triana, selaku Koordinator Program Studi Teknik Material dan Metalurgi di Institut Teknologi Kalimantan ITK Karangjoang. ITK ini memiliki 10 prodi, yang salah satunya adalah Prodi Teknik Material dan Metalurgi di bawah jurusan Ilmu Kebumian dan Lingkungan, di mana prodi ini mempelajari tentang sifat bahan, sifat kimia, dan sifat fisikanya terhadap logam, plastik, keramik, dan lain sebagainya, dan aplikasi pada berbagai bidang. Yang ada di Prodi Teknik Material Metalurgi yaitu beberapa kegiatan yang menunjang kemampuan akademik dan non-akademik mahasiswa, seperti pengajaran. Jadi dalam pengajaran ini kami menggunakan kurikulum yang memang kurikulum tersebut sudah disesuaikan dengan kebutuhan industri, aplikasi berbagai bidang material, seperti itu. Kemudian yang kedua, mahasiswa dibekali dengan praktikum di laboratorium. Tentunya mereka tidak hanya mendapatkan teori, tapi mereka juga praktek. Contohnya praktek teknologi cor, logam, atau teknologi las. Kemudian ada studi ekskursi, di mana studi ekskursi ini mahasiswa dibawa ke beberapa perusahaan untuk melihat secara langsung apa saja aplikasi material di bidang-bidang tertentu. Selain studi ekskursi ada juga kuliah lapangan, sama tujuannya seperti studi ekskursi, namun studi ekskursi ini cakupannya lebih luas daripada kuliah lapangan. Kemudian ada kerja praktek, di mana mahasiswa semester 6 atau 7 itu diwajibkan untuk menjalani kerja praktek di sebuah perusahaan untuk mengaplikasikan ilmu yang sudah dia dapatkan di Prodi Teknik Material dan Metalurgi ITK. Baik, di Prodi Teknik Material dan Metalurgi di ITK sendiri memiliki 4 bidang konsentrasi. Yang pertama yaitu korosi dan analisa kegagalan, di mana kita tahu korosi merupakan sesuatu hal yang merugikan, dan di teknik material ini kita lebih mendalami kepada pengendalian korosi yang ada di industri minyak dan gas bumi. Kemudian yang kedua yaitu proses metalurgi manufaktur, di mana di dalam bidang konsentrasi ini dikaji lebih dalam mengenai teknologi las dan teknologi cor logam. Kemudian yang ketiga ada ekstraksi metalurgi, di mana ekstraksi metalurgi ini mempelajari bagaimana pengolahan logam setelah diambil dari alam. Jadi lebih kepada pengolahan logamnya untuk dijadikan bahan pakai. Seperti itu. Kemudian yang terakhir yaitu bidang material inovatif. Nah, material inovatif ini lebih dikaji lebih dalam lagi mengenai polimer, kemudian keramik, kemudian berbagai macam plastik yang material-material ini diaplikasikan pada berbagai bidang dan bermanfaat untuk kehidupan sehari-hari, seperti itu. Baik, lulusan Teknik Material dan Metalurgi di Institut Teknologi Kalimantan diharapkan memiliki beberapa uji kompetensi di bidang Teknik Material dan Metalurgi. Ada 3 yang kami harapkan lulusan ini mampu untuk melakukan uji kompetensi ini. Yang pertama yaitu uji mekanik pada logam, yang kedua yaitu karakterisasi material, yang ketiga yaitu uji korosi dan pengendalian korosi. Yang pertama yaitu uji mekanik pada logam, di mana pada uji mekanik pada logam, mahasiswa kami tuntut untuk memiliki kompetensi yaitu uji tarik atau tensile test, di mana pengujian dilakukan untuk mengetahui kekuatan, keuletan, dan elastisitas suatu logam. Pengujian ini memakai standar ASTM E8 atau standar-standar lain yang memang memenuhi standar pengujian uji tarik. Yang selanjutnya yaitu uji tekuk atau bend test, di mana pengujian yang dilakukan untuk mengetahui modulus elastisitas suatu logam. Pengujian ini memakai standar ASTM E290 atau standar yang relatif sama standarnya untuk uji tekuk atau bend test. Kemudian uji lelah atau fatigue test, di mana pengujian yang dilakukan untuk mengetahui ketahanan material terhadap beban siklik atau terus-menerus. Pengujian ini memakai standar ASTM E606. Selanjutnya yaitu uji kekerasan atau hardness test, di mana pengujian yang dilakukan untuk mengetahui kekerasan suatu logam yang berpengaruh pada sifat ketahanan aus suatu logam. Kemudian yang terakhir yaitu uji impact atau impact test, di mana pengujian yang dilakukan untuk mengetahui kemampuan material menyerap energi dan ketahanan terhadap beban kejut. Pengujian ini memakai standar ASTM E23. Kemudian selanjutnya yaitu karakterisasi material, di mana yang pertama ada uji metalografi, pengujian yang dilakukan untuk mengetahui struktur mikro suatu logam dengan perbesaran hingga 1000 kali. Pengujian ini memakai standar ASTM E3. Selanjutnya yaitu X-ray diffraction. X-ray diffraction untuk menguji fasa suatu material. Selanjutnya yaitu Fourier transform infrared spektroskopi atau FTIR, di mana pengujian dilakukan untuk mengetahui gugus fungsi atau ikatan suatu material. Selanjutnya yaitu pengujian yang paling populer di bidang penelitian, yaitu scanning electron microscope atau SEM, di mana pengujian dilakukan untuk mengetahui morfologi suatu permukaan hingga perbesarannya. Yang terakhir yaitu EDX, Energy Dispersive X-ray Spectroscopy, di mana pengujian dilakukan untuk mengetahui perbesaran unsur pada suatu material. Yang terakhir yaitu uji korosi dan pengendaliannya, di mana uji korosi menggunakan dua metode, yaitu OCP dan salt spray. OCP atau Open Circuit Potential, yaitu pengujian yang dilakukan untuk mengetahui laju korosi pada logam. Sementara salt spray, yaitu pengujian yang dilakukan untuk mengetahui laju korosi pada logam di lingkungan air laut.
Oke, selamat siang Pak Nofrijon. Oh iya.
Selamat siang, Pak Jatmoko.
Oke, Pak. Gimana kabarnya, Pak?
Alhamdulillah sehat. Gimana? Apa kabar di sana? Sehat ya semua ya?
Sehat, Pak. Semuanya alhamdulillah. Mudah-mudahan lancar. Terima kasih, Pak, waktunya, Pak.
Sama-sama. Ini sudah dimulai atau bagaimana?
Belum, Pak.
Okay.
Tepat jam 2. Ini kita lagi persiapan. Jadi sesi pemutaran video dulu, nanti habis itu ada nanti masuk ke moderator dan MC kegiatan jam 2 pas. Ya, terima kasih Pak.
Terima kasih sama-sama. Jadi saya videonya saya tutup sama mikrofon. Oke, terima kasih.
Selamat datang di ruang kelas kampus Institut Teknologi Kalimantan. Mata kuliah kita kali ini adalah pengenalan program studi Teknik Material dan Metalurgi.
Pernah terpikirkan tidak, mengapa gigi palsu bisa aman dipasang pada rahang seseorang bertahun-tahun lamanya? Kenapa motor kuat menahan beban kita yang berpuluh-puluh, bahkan beratus-ratus kilogram beratnya? Apakah material laptop ini sama dengan motor tadi?
Kayaknya nggak kuat deh materialnya.
Sadar atau tidak, perkembangan HP dari zaman dulu hingga zaman sekarang semakin canggih, tapi semakin ringan. Kok bisa dari kebutuhan kacamata yang tebal untuk minus diganti dengan plastik tipis yang disebut softland? Sadar atau tidak, kemajuan teknologi berangkat dari perkembangan material. Pertama-tama, kita menemukan besi atau metal di alam, lalu kita menemukan plastik atau polimer, sampai akhirnya kita menemukan keramik. Tidak cukup dengan ketiga jenis material yang berdiri sendiri-sendiri, kemudian kita menggabungkannya dan ditemukanlah komposit. Kemudian pertanyaannya berubah dari bagaimana kita memanfaatkan material ini menjadi bagaimana cara kita menemukan material baru dengan karakter yang lebih baik dari material yang telah ada. This is your Materials and Metallurgical Engineers Group. Kami merekayasa material. Program Studi Teknik Material dan Metalurgi Institut Teknologi Kalimantan atau ITK telah terus meningkatkan kegiatan pembelajaran sains dan teknologi untuk rekayasa material sejak tahun 2013. Berdiri di bumi etam Kalimantan yang berlimpah potensi dan kekayaan sumber daya alam, program studi Teknik Material dan Metalurgi ITK terus berkembang untuk menciptakan terobosan-terobosan rekayasa material. Telah mendapatkan akreditasi B oleh BAN PT Program studi Teknik Material dan Metalurgi ITK selalu berusaha agar semakin baik dari masa ke masa. Program studi ini memiliki visi untuk menghasilkan kompetensi unggul dalam bidang rekayasa material dan metalurgi di wilayah Kalimantan pada tahun 2025. Dalam perjalanannya, program studi Teknik Material dan Metalurgi ITK terus mengembangkan fasilitas penunjang kegiatan belajar mengajar yang lebih baik, termasuk laboratorium yang semakin terdepan dalam menyediakan layanan penelitian dan pengembangan riset. Hingga tahun 2020, terdapat 10 dosen dan 2 staf untuk membantu pembelajaran 300 mahasiswa di program studi ini. Kolaborasi penelitian juga dikembangkan melalui network antar institusi. Program studi Teknik Material dan Metalurgi ITK akan terus berkembang untuk melahirkan sumber daya manusia yang unggul dalam kompetensi bidang rekayasa material dan teknologi bahan, tidak hanya demi kemajuan industri, melainkan juga pengabdian masyarakat yang berkualitas.
Demikian pengenalan program studi Teknik Material dan Metalurgi. Sampai jumpa di pertemuan selanjutnya.
Diawali dari keinginan pemerintah Indonesia untuk memenuhi kebutuhan sumber daya manusia di luar Pulau Jawa, berdirilah sebuah perguruan tinggi negeri di jantung kota Balikpapan bernama Institut Teknologi Kalimantan. Diresmikan oleh Presiden Republik Indonesia ke-6, Susilo Bambang Yudhoyono pada tanggal 6 Oktober 2014, Institut Teknologi Kalimantan memulai kegiatan akademik dengan menerima mahasiswa baru sejak tahun 2012. Dan terhitung sejak 5 September 2019, jumlah mahasiswa Institut Teknologi Kalimantan adalah sebanyak 4.074 mahasiswa. Desain infrastruktur, pengelolaan sumber daya air, dan manajemen proyek konstruksi dipelajari dalam program studi teknik sipil. Identifikasi potensi masalah wilayah dan kota, serta menyusun rencana tata ruang didalami dalam program studi perencanaan wilayah dan kota. Pada program studi matematika, selain mempelajari aljabar, geometri, dan analisis, matematika juga berpeluang untuk mempelajari statistika, komputasi, aktuaria, dan riset operasi. Institut Teknologi Kalimantan juga menginginkan lulusan yang dapat berperan menjadi konsultan dan sistem integrator, database specialist, dan IS academician yang dilatih dalam program studi sistem informasi. Prodi Informatika mempelajari bidang dasar informatika, pemrograman komputer, serta mampu mendayagunakan, mengevaluasi, dan mengidentifikasi pengembangan sistem berbasis
Halo guys, perkenalkan, nama aku Saskia Dian Olianur. Sekarang aku berada di Institut Teknologi Kalimantan atau ITK. Di sini aku ditemani dengan Kak Febi.
Halo semua, perkenalkan saya Febi Trijulianti dari mahasiswa Institut Teknologi Kalimantan angkatan 2018.
Nah Kak, aku kan mahasiswa baru nih. Kakak bisa nggak bawa aku keliling-keliling ITK? Pasti penonton juga pada penasaran kan?
Nah, saat ini kita lagi berada di gedung A lantai 1. Pertama kali kalian masuk, kalian akan bertemu dengan aula.
Nah, aula ini buat apa sih Kak? Kok banyak meja-meja gitu?
Nah, aula ini digunakan oleh mahasiswa Institut Teknologi Kalimantan untuk beristirahat, bersantai, dan juga ngobrol-ngobrol.
Nah, Kak, selain aula tadi, di gedung A lantai 1 ini ada apa aja sih, Kak?
Nah, selain ada aula, di sini juga ada laboratorium kimia dan juga UPT. UPT ini berfungsi untuk menunjang kinerja ITK, di mana terdiri dari 3, yaitu UPT TIK, UPT Bahasa, dan UPT Perpustakaan. Yuk kita mampir dulu ke UPT Perpustakaan.
Oke. Nah, di sini banyak banget ya Kak buku-bukunya, terus juga kayaknya lengkap.
Nah iya, di sini banyak banget buku yang dapat menunjang perkuliahan kita, mulai dari matematika, fisika, kimia, statistik, teknik sipil, dan banyak lainnya.
Terus selain buku-buku di sini ada apa aja sih Kak?
Nah di sini kalian juga bisa nyari referensi untuk tugas akhir dan kerja praktik.
Oh gitu. Terus tadi di situ aku ada di corner. Itu apa?
Nah di corner itu mencakup buku-buku tentang kebang sentralan khususnya di Balikpapan.
Wah, nyaman banget ya di sini. Kayaknya aku bakal sering-sering belajar ke sini deh, Kak. Soalnya juga adem.
Nah, bener banget. Tapi selain itu, kalian juga bisa mengakses perpustakaan melalui website perpustakaan.tk.ac.id, di mana ada banyak banget e-jurnal, e-book, repositori tugas akhir, dan kerja praktik.
Oh iya, Kak. Ayo kita keliling lagi.
Ayo.
Nah, guys. Sekarang aku ada di lantai 2 gedung A. Oh iya Kak, itu apa sih?
Nah, kalau itu adalah loket pelayanan akademik dan kemahasiswaan.
Gunanya loket ini buat apa sih Kak?
Nah, loket ini digunakan mahasiswa untuk mengurus berkas-berkas, di mana ada loket 1, loket 2, loket 3, dan loket 4, sesuai berkas apa yang kalian butuhkan.
Oh gitu ya.
Itu yuk, ayo. Nah, jadi sekarang kita lagi ada di ruang rektorat nih, di mana merupakan ruangan dari rektor, wakil rektor, dan jajaran.
Oh ya, di situ ada ATM sama bank juga ya Kak?
Benar banget, di sini ada bank dan ATM untuk mempermudah mahasiswa untuk menabung, mengambil uang, dan juga mentransfer.
Nah guys, jadi kalau kalian lapar, terus kehabisan uang, kalian bisa ngambilnya di sini.
Yuk masuk.
Selamat datang di ruang kelas kampus Institut Teknologi Kalimantan. Mata kuliah kita kali ini adalah pengenalan program studi Teknik Material dan Metalurgi.
Pernah terpikirkan tidak, mengapa gigi palsu bisa aman dipasang pada rahang seseorang bertahun-tahun lamanya? Kenapa motor kuat menahan beban kita yang berpuluh-puluh, bahkan beratus-ratus kilogram beratnya? Apakah material laptop ini sama dengan motor tadi?
Kayaknya nggak kuat deh materialnya.
Sadar atau tidak, perkembangan HP dari zaman dulu hingga zaman sekarang semakin canggih, tapi semakin ringan. Kok bisa dari kebutuhan kacamata yang tebal untuk minus diganti dengan plastik tipis yang disebut softland? Sadar atau tidak, kemajuan teknologi berangkat dari perkembangan material. Pertama-tama, kita menemukan besi atau metal di alam, lalu kita menemukan plastik atau polimer, sampai akhirnya kita menemukan keramik. Tidak cukup dengan ketiga jenis material yang berdiri sendiri-sendiri, kemudian kita menggabungkannya dan ditemukanlah komposit. Kemudian pertanyaannya berubah dari bagaimana kita memanfaatkan material ini menjadi bagaimana cara kita menemukan material baru dengan karakter yang lebih baik dari material yang telah ada. This is your materials and metallurgical engineers work. Kami merekayasa material. Program Studi Teknik Material dan Metalurgi Institut Teknologi Kalimantan atau ITK telah terus meningkatkan kegiatan pembelajaran sains dan teknologi untuk rekayasa material sejak tahun 2013. Berdiri di bumi etam Kalimantan yang berlimpah potensi dan kekayaan sumber daya alam, program studi Teknik Material dan Metalurgi ITK terus berkembang untuk menciptakan terobosan-terobosan rekayasa material. Telah mendapatkan akreditasi B oleh BAN PT, program studi Teknik Material dan Metalurgi ITK selalu berusaha agar semakin baik dari masa ke masa. Program studi ini memiliki visi untuk menghasilkan kompetensi unggul dalam bidang rekayasa material dan metalurgi di wilayah Kalimantan pada tahun 2025. Dalam perjalanannya, program studi Teknik Material dan Metalurgi ITK terus mengembangkan fasilitas penunjang kegiatan belajar mengajar yang lebih baik, termasuk laboratorium yang semakin terdepan dalam menyediakan layanan penelitian dan pengembangan riset. Hingga tahun 2020, terdapat 10 dosen dan 2 staf untuk membantu pembelajaran 300 mahasiswa di program studi ini. Kolaborasi penelitian juga dikembangkan melalui network antar institusi. Program studi Teknik Material dan Metalurgi ITK akan terus berkembang untuk melahirkan sumber daya manusia yang unggul dalam kompetensi bidang rekayasa material dan teknologi bahan, tidak hanya demi kemajuan industri, melainkan juga pengabdian masyarakat yang berkualitas.
Demikian pengenalan program studi Teknik Material dan Metalurgi. Sampai jumpa di pertemuan selanjutnya. Selamat datang di ruang kelas kampus Institut Teknologi Kalimantan. Mata kuliah kita kali ini adalah pengenalan program studi Teknik Material dan Metalurgi.
Pernah terpikirkan tidak, mengapa gigi palsu bisa aman dipasang pada rahang seseorang bertahun-tahun lamanya? Kenapa motor kuat menahan beban kita yang berpuluh-puluh, bahkan beratus-ratus kilogram beratnya? Apakah material laptop ini sama dengan motor tadi?
Kayaknya nggak kuat deh materialnya.
Sadar atau tidak, perkembangan HP dari zaman dulu hingga zaman sekarang semakin canggih, tapi semakin ringan. Hai Kak. Kok bisa dari kebutuhan kacamata yang tebal untuk minus diganti dengan plastik tipis yang disebut softland? Sadar atau tidak, kemajuan teknologi berangkat dari perkembangan material. Pertama-tama, kita menemukan besi atau metal di alam, lalu kita menemukan plastik atau polimer, sampai akhirnya kita menemukan keramik. Tidak cukup dengan ketiga jenis material yang berdiri sendiri-sendiri, kemudian kita menggabungkannya dan ditemukanlah komposit. Kemudian pertanyaannya berubah dari bagaimana kita memanfaatkan material ini menjadi bagaimana cara kita menemukan material baru dengan karakter yang lebih baik dari material yang telah ada. This is your Materials and Metallurgical Engineers World. Kami merekayasa material. Program Studi Teknik Material dan Metalurgi Institut Teknologi Kalimantan atau ITK telah terus meningkatkan kegiatan pembelajaran sains dan teknologi untuk rekayasa material sejak tahun 2013. Berdiri di bumi etam Kalimantan yang berlimpah potensi dan kekayaan sumber daya alam, program studi Teknik Material dan Metalurgi ITK terus berkembang untuk menciptakan terobosan-terobosan rekayasa material.
Institut Teknologi Kalimantan, kokoh berdiri di Katulistiwa, simbol suci kemajuan teknologi.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Respectable Director of Institute Teknologi Kalimantan, Profesor Budi Santosa, PhD. Excellencies, the Vice Rector of Academic Affairs of Institute Teknologi Kalimantan, Nurul Widyastuti, SSI, MSI, PhD. Excellencies, the Vice Rector of Non-Academic Affairs of Institute Teknologi Kalimantan, Dr. Muhammad Mazhuri, MT. The honorable speakers, Professor Yasuaki Einaga from Keio University, Professor Masato Tominaga from Saga University, and Dr. Nofrijon from Universitas Indonesia. All of the invited guests from the officials of Institute Teknologi Kalimantan, researchers, colleagues, and students from various institutions. Ladies and gentlemen, welcome to the International Webinar Series, Recent Technology on Material Science and Engineering. My name is Gusti Umindia Nurtajala, and of course, it is my pleasure to be a master of ceremony in a beautiful day. Now, behalf on Department of Materials and Metallurgical Engineering of Institute Teknologi Kalimantan, who organized this event perfectly, I would like to extend a very warm welcome to all of you. We appreciate you taking the time of your busy schedule to join us today. I will deliver the rundown for today. First, opening. Second, sing Indonesia Raya, a national anthem of Indonesia. Third, welcoming speech from Rector of Institute Teknologi Kalimantan, Profesor Budi Santosa, PhD. Fifth, speech and discussion session. The last but not least, closing. Before we continue to the main agenda, let us sing and listen together the national anthem Indonesia, Indonesia Raya.
Indonesia tanah airku, tanah tumpah darahku. Di sanalah aku berdiri, jadi pandu ibuku. Indonesia kebangsaanku, bangsa dan tanah airku. Marilah kita berseru, Indonesia bersatu. Hiduplah tanahku, hiduplah negeriku, bangsaku, rakyatku semuanya. Bangunlah jiwanya, bangunlah badannya, untuk Indonesia Raya. Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang kucinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya. Indonesia Raya, merdeka, merdeka, tanahku, negeriku yang kucinta. Indonesia Raya, merdeka, merdeka, hiduplah Indonesia Raya.
Thank you for your attention. First of all, I would like to introduce our beloved campus, Institute Teknologi Kalimantan, and also Department of Materials and Metallurgical Engineering. Institut Teknologi Kalimantan has established since 2014. In 2020, we have 17 departments with 145 lecturers and 5,089 students. Institut Teknologi Kalimantan is located in Balikpapan, East Kalimantan, Borneo Island, Indonesia. We have already received an official accreditation with B accreditation. One of the seven departments in ITK, Materials and Metallurgical Engineering, become one of the emerging departments that always eager to develop. We also have B for the national accreditation, which make us desire to improve into the better place for study. Materials and Metallurgical Engineering is an interdisciplinary field that learns about how to design materials for creating functional products. In 2020, we consist of 10 lecturers with various research interests such as welding, corrosion behavior and prevention, nanomaterial and porous materials, biomaterials, polymer, and composite. Also, we have 418 students in total. We are also honored having collaboration with Universitas Indonesia in 2017 and Saga University in 2020. Several industries and companies also has become our partner for academic and research purposes. For example, PT Komatsuri Manufacturing Asia and PT Universal Tekno Reksajaya. For the next collaboration, we expect that we could have cooperation with Keio University. And now, to formally kick off our event, it's my pleasure to invite the Rector of Institut Teknologi Kalimantan, Professor Budi Santosa, PhD, to deliver an opening speech. Please welcome Professor Budi Santosa, PhD. Time is yours.
Good afternoon, everybody.
Good afternoon.
To the honorable speakers. First, Professor Yasuaki Einaga from Keio University. And the second honorable speaker, Professor Masato Tominaga from Saga University. And the third, Dr. Nofrijon yang terhormat dari Universitas Indonesia. Welcome to Institut Teknologi Kalimantan. Even though this is the online webinar, but we hope that this event can give strong knowledge and new insight about material science and engineering. So in the midst of COVID-19 outbreak, we still can hold very important agenda, international seminar on recent technology on material science and engineering. I'm very grateful for the local committee for holding this seminar. And thank you very much for the honorable speakers from Japan and from Universitas Indonesia. This is the form of our cooperation between ITK and Keio and Saga, and also with University of Indonesia. We hope that this is not the first cooperation between us. We hope that in the next time we can hold another cooperation. Maybe we can do some research collaboration in other agenda like student exchange, or we can do other international seminar offline. Yeah, after the COVID-19 go away, we can hold another seminar. So by mention Bismillahirrahmanirrahim, I open this seminar formally. I hope that this seminar will give much beneficial for students, especially, and also for the lecturer in ITK, Institut Teknologi Kalimantan. And I hope that the student will give attention through the whole event. So you have to follow the speak seriously until this event finish. So don't leave before the event is finished. Okay, I think that's all from me as a rector of ITK. So once again, I hope this seminar will give very beneficial things for our students, our lecturer. Thank you.
Thank you very much for the opening speech, Professor Budi Santosa, PhD. Before we continue, please, we do a photo session. To the committee. To the committee who in charge, please, we do a photo session before we continue the next agenda. To the committee, has been done? Have you been taking a picture? Please wait a minute. Okay, I will count 1, 2, 3 and pause. Everybody stand by. 1, 2, 3. Okay, once again, with another pose, it's okay. 1, 2, 3, smile. Okay, thank you. To provide comfortable situation during webinar, we kindly deliver you some information. First, participants are forbidden to open the camera and unmute during the webinar unless Q&A session with the host permission. Participants are required to change the name during the webinar with the exact name and institution as on registration form. For example, Novita Triasih STP MSc _ Institut Teknologi Kalimantan. Third, participants are allowed to ask questions through the chat on Zoom meetings, to host or MC, or use the raise hand feature. Fourth, the e-certificate will be given to the participants who fill out an attendance that will be shared at the end of the event. Without further ado, I will invite the moderator of today who will lead the speech and discussion session. Here I will read the curriculum vitae of the moderator. The moderator today is Yunita Triana SSE MSE. She is a lecturer of Materials and Metallurgical Engineering ITK. She is also PhD candidate at Graduate School of Integrated Design Engineering Keio University. Research interest, analytical chemistry, biosensor and sensor, electrochemistry, and corrosion. Formal education, bachelor degree in Universitas Mula Warman, master degree in Institut Teknologi 10 November, and PhD candidate in Keio University, ongoing. She also received grants from ASEA Uninet Research Funding in 2017. Research funding for young lecturer from Ministry of Research, Technology, and Higher Education Indonesia in 2018. And dissertation grant from Lembaga Pengelola Dana Pendidikan LPDP Indonesia in 2019. So please welcome Yunita Triana, MSE.
Okay, thank you very much for your nice opening, Miss Gusti. Everybody can hear my voice?
Sure.
Okay.
Very clear.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone. Your Honorable Professor Budi Santoso, PhD, management team, lecturers, staffs, and students of Institut Teknologi Kalimantan. Your Honorable all the speakers and participants. It's very nice to see you all in this online event today. Allow me to be your moderator of the first international webinar arranged by MME ITK. As Miss Gusti told you in my CV that I'm a lecturer in MME Department ITK and now continuing my PhD student at Graduate School of Integrated Design Engineering, Keio University. I feel so honored to accept this chance from the committee to be your moderator today. First of all, I would like to explain the rules of our discussion today. First, the participants can give the questions in the chat menu along the speech time. So you can give your question in the chat menu along the speech time. Second, the questions can be in Bahasa Indonesia. I will translate it in English to the speakers. So you can also write the question in Bahasa Indonesia in our language, and I will translate it to English to the speakers. Then, third, the participants may do the raise hand in the discussion time. So I will open a chance to you, to the participants, to use the raise hand menu to talk directly to the speakers later. Okay. We have 3 speakers to explore more about the topic today. The topic today is recent technology on materials science and engineering. We have 3 speakers here, Professor Dr. Yasuaki Einaga from Keio University, Professor Dr. Masato Tominaga from Saga University, and the third is Dr. Nofrijon Sofyan from Universitas Indonesia. How are you, sir? We are very happy to have expert people such all of you in materials field. We know all of you have a tight schedule, but accepting our offering to be speaker in our first international webinar is much honor for us. Thank you very much to attend this webinar, to be a speaker and sharing your information, your valuable information, knowledge today to us. Okay, we will enter the speech session. This is the next session. To shorten the time, let us start from our first speaker, Professor Einaga. I will give explanation about his background. The committees, please perform the slide. Okay. This is our first speaker today. The complete name is Professor Dr. Yasuaki Einaga, and his formal educations from bachelor degree, master degree, and PhD degree got from the University of Tokyo. And the current position now is the full professor of Department of Chemistry, Keio University. And about the research interests, he is focused on functionally material science, electrochemistry, photochemistry, and also diamond electrochemistry. And about the awards, he has got so many awards. 2016, he got the Ichimura Prize in Science for Distinguished Achievement. In the same year, he got the Chemical Society of Japan Award for Creative Work for 2015. And 2011, he got the Cow Research Initiative Award. And also in 2008, he got the APA Prize for Young Scientists. And the last is 2005, he got the Chemical Society of Japan Award Young Chemist for 2004. So many awards. Okay, he's very good in the field. So to start on the time, Prof. Einaga, please, time is yours to give the lecture.
Okay, can you hear me?
Yes, I can hear your voice clearly, sir.
Okay, so thank you very much, Nita Sensei, for nice introduction. Selamat siang, everyone. Good afternoon, everyone. My name is Einaga from Keio University, Japan. First of all, I'd like to say thank you again for giving me a chance to talk in this nice webinar, especially Gusti Sensei for the nice preparation, and for organizing committee, for everyone. I want to thank you. Okay, so first, anyway, I want to start now. Okay, can you see this slide? Okay. Okay. So today the time is limited. So anyway, I'd like to talk about our recent work of the talk about the electrochemical application of boron-doped diamond electrode. Okay. So anyway, we are focusing on boron-doped diamond, and as you know, diamond is an insulator. Everybody knows. But when boron is doped into the diamond, the conductivity increases. When the boron is doped in very low concentration, this shows a semiconductor. So these studies are very popular. Many people are studying insulating diamond and semiconducting diamond are done by many people. Okay, so as you know, the diamond is used as a drill or cutter. This is no need to show the conductivity. Insulator is okay. So there are many studies. On the other hand, when the doping level is higher like this, 0.1% to 1%, this conductivity increases to like metal-like conductivity like this. So we are focusing on this area. So, and we focus on this material as an electrode material. This is our research, okay? So how to make diamond? This is our CVD machine, our microwave plasma assisted CVD machine we have in our lab. And this is very simple. So by using the acetone, this is a carbon source. And the trimethylboron, this is a boron source. This is a liquid boron source and a liquid carbon source, just mixed. And when we control the concentration, we can control the conductivity from insulator to metal-like conductivity. And by using this CVD method, we could make the boron-doped diamond on the substrate. This is a SEM image of the polycrystalline boron of diamond. This shows the conductivity. Okay. So by using this boron of diamond, we are applying many applications from 2000. From 2000, we mainly focused on a sensor application, like analytical purpose, like this environmental sensor or biomedical sensors. First, I want to show the example of this application. Why diamond electrode? Why boron of diamond electrode is good? Because there are many good electrochemical properties like this. This is maybe most of you know well about the electrochemistry, I hope. When this is a conventional electrode, glassy carbon, gold, and platinum. As you can see, when these conventional electrode is used, when we apply it to the 1 point several volt like this, and oxygen evolution start. On the other hand, when we apply the negative potential like minus 0 several volt, hydrogen evolution start. So this is potential window, you know. When we use the boron of diamond electrode, as you can see, the oxygen evolution start very high potential, and hydrogen also difficult to occur. So this is a very good property of the wide potential window. And the background current is also very low. And also physically and chemically stable is the most another important factor because of the diamond material. And active species generation also important, but I will explain a little later. Okay, so this is a typical example for the electrochemical analysis application for sensor application. This is a typical example of the histamine detection. You know histamine. Histamine is a very important when you know the allergy comes. For example, recently in Japan, in spring season, the pollen allergy is very, very popular. You know, kahunshou, very, very popular. So in that case, the histamine can cause the sneeze or something like that. So in order to detect this histamine, for example, when we use the glassy carbon, this is a typical conventional electrode. Glassy carbon is used as you can see, the oxygen evolution start like this. This is without histamine, and this is with histamine. As you can see, with histamine, we can see some oxidation reaction around here, but oxygen evolution is also shown around this potential. So this is very difficult to know the concentration of histamine. On the other hand, when our boron of diamond is used, as you can see, the oxygen peak of the histamine is shown like this very clearly, and the background current is very low, so the signal to background is very high, so the sensitivity is very nice. This is a typical example. Okay, so not only the histamine, but some this is another example of the chlorine detection. Chlorine also very nice because when we use conventional electrodes such as glassy carbon, platinum, gold, as you can see, the oxygen evolution is observed around here. On the other hand, when a boron of diamond electrode is used, the best very clear peak is observed, no oxygen evolution. So this is a very nice. And this is a reaction of the HClO minus oxidation. And this is this current is shown the concentration dependence. As you can see, the linear beautiful calibration curve is observed even in a very low concentration like 0.2 ppm. It means we can apply to the tap water analysis or the swimming pool analysis also possible. So anyway, after this report, we reported this one in almost more than 10 years ago, but recently, our collaborating company produced the prototype of the chlorine sensor. And maybe you know, recently the COVID situation, COVID-19 situation, the chlorine is very, very important to disinfect, the washing hand or something. The chlorine compound is very important. So recently, this product is also very becoming popular. Okay, this will be commercially available very, very soon. Okay, so I want to introduce another example of the sensor application. This is the microelectrode. Boron doped diamond microelectrode. Microelectrode is a very small electrode. This is a diamond microelectrode. The size is very small. So the microelectrode shows a very nice, remarkable electrochemical property like this. And not only these properties, but also this electrode can apply to in vivo detection for medical application. Okay. So just today, the time is limited, so I want to introduce the very recent one example of the application of the simultaneous detection of pharmacokinetics. So this is a drug of the bumetanide is a drug. This one is used as a loop diuretic drug, Renewable in Japanese. So a loop diuretic drug, but this one can show the side effect of hearing loss. This is well known. So what we want to know is that the relationship between the drug concentration and the hearing ability. When the drug comes to the ear, the hearing ability decreases. It is true or not? This is the purpose. Okay. So in the beginning, we check the electrochemistry of the bumetanide, this drug. As you can see, this is the oxidation of the bumetanide, and this is very clear because observed by using diamond. So other electrode is impossible to detect. So diamond is very nice. Then this is in vivo detection. We collaborate with a medical school, and this is our boron diamond microelectrode, and this is a glass electrode. By this diamond electrode, the drug concentration is monitored, and by this glass electrode, the hearing ability is monitored by this endolymph potential. So this simultaneously we monitor this one, this signal, and then injection of drug. So this is the result of the real-time measurement. As you can see, the before injection, the bumetanide concentration is 0 like this. On the other hand, this hearing ability is very nice, plus 80 millivolt is normal. And here, the bumetanide drug is injected. And then 1 minute later, the drug comes to the ear. And in the ear, the bumetanide comes. At the same time, the hearing ability decreases. This kind of relationship between the function and the concentration is observed directly in real time. This is an example. Okay, the time is, I have more 10 minutes, okay? Okay, so now I show the example of the sensor application, but now from 2011, in these 10 years, we expand the application not only for sensor, but also some other application like wastewater treatment, CO2 reduction, electrochemical organic synthesis, and electrochemiluminescence. So many other applications, especially for improving the environment. Not only that application, but also the fundamental study is also very important. Okay, so today time is limited, so just I want to introduce the recent application of the CO2 reduction. Okay. So the carbon dioxide reduction is a very, very important topic in the world recently. You know, the CO2 can be converted to the very useful compound like fuel or plastic or something like that. So this is the very simple method. Okay. So this electrochemical reduction of carbon dioxide was very popular from the very old time. You know, many people are interested in this topic. However, so far, there are many people study the CO2 reduction by some conventional electrode like lead, silver, zinc, or something like that. but always the hydrogen evolution is a competing with the CO2 reduction. CO2 reduction to this compound is okay, but the hydrogen evolution can interfere. You know, this is not good. And not only that, but stability of the electrode was also a problem. So anyway, we tried to use boron diamond. As I showed you before, the potential window is very big, so it means hydrogen evolution is also can be suppressed like this. So we expect the high efficiency of the CO2 reduction is possible. Okay, so this is the first result in 6 years ago. As you can see, this is a conventional electrode, and surprisingly, when we use boron diamond, the formaldehyde was produced with very high efficiency at room temperature and ambient pressure. This was a very surprising data for us. And after that, the many people are interested in CO2 reduction by using the diamond electrode. And then we, now also we are very focusing on this topic. So now I want to show the recent trial for the CO2 reduction. One direction is the 100% Faraday efficiency. So it means, and after that we studied many, and then finally, recently we achieved the 100% Faraday efficiency by using this condition, and by using this current density, we optimize the condition. Then CO2 to formic acid was very easy to obtain by using boron diamond. And by using this flow cell system, we designed this flow cell system, and finally we could achieve the almost 100% Faraday efficiency. So it means that all of the electricity is used for the CO2 reduction to produce formic acid. This is a recent result. And another direction is to produce more variable compound. For example, to control the product, not only formic acid or formaldehyde, we want to produce more variable compound. So this is another direction. So in order to produce the other material, we try to make the metal modified boron diamond like this. This is a result of the copper modified boron diamond. By using this copper modified diamond, this particle is copper on the boron diamond surface. And by using this one, acetaldehyde was ethanol acetone C2, C3 compound were produced. This is good because of the catalytic activity of the copper. Okay. So another direction is amine solution. Amine is very important for the carbon capture system. The CO2 is absorbed in this solution. So to check this property, we use ammonia, and in ammonia, carbon dioxide is dissolved. Then what happened by the reduction of this amine solution is an ammonia solution. And surprisingly, the methanol is produced. So this is an interesting topic. And we studied, today I don't have enough time, but we studied the fundamental very carefully, the pH dependence or something like that. And then pH is also important. Anyway, by using the copper modified BDD, we produce methanol. Okay, the another direction is to control by electrolyte. And first, we change the cation like lithium, sodium, potassium, rubidium, cesium. As you can see, in case of cesium, rubidium, potassium, we could obtain the formic acid, but when sodium, lithium case, the formic acid decrease. This is too bad, but this is due to the buffer effect of the alkali cation. This is discussed by this paper, and by using this cation, the pH near the local pH is changed due to the buffer effect. So anyway, the pH change is important for the production. This is okay, the cation effect. And then we change the anion control like this. And surprisingly, when we found when we use perchlorate is used, carbon monoxide is produced like this. No carbon monoxide, always formic acid are produced, as I told you. And here, carbon monoxide is produced. This is a new point. And then we optimize the condition. And this data is a little bit old. Recently, we optimize the condition. Then now we achieve the 70% of the Faraday efficiency of the carbon monoxide now. Now, this is 1 year ago. The first data shows 30% of the carbon monoxide, but now 70% is possible. Anyway, when we control the anion, as you can see, that we can control the product. For example, if we want to get carbon monoxide, we should use perchlorate, and when we want to get the formic acid, we should use KCl solution. Okay, so another important result is fundamentals. You know, the CO2 is reduced to CO2 anion radical first, and then someone discussed how to control the product. Someone said it is discussed the interaction between the CO2 anion radical and the electrodes is important. For example, the interaction is strong, this should be carbon monoxide. The interaction is weak, the formic acid is produced. This is discussed. However, there's no evidence. So we try to study detail directly by using the in situ ATR-IR system. And by using this one, we could directly observe the intermediate, and we could observe the difference between this perchlorate and chlorine anion. And this is peak shift is observed between them. And another experiment was the carbon-13 boron diamond is prepared, and then this IR also support the mechanism. Anyway, we could directly observe the interaction between the intermediate and the electrode surface. So this is due to the control of the product. Okay, finally, we could succeed to succeed the selective production by carbon monoxide, carbon dioxide reduction. Okay. So finally, this is a future direction. Actually, almost 10 years ago, I made this image, and I prepared this one 10 years ago, and I said in the future I want to realize these application. But now, as I told you, the detection of chlorine is become commercially available, and chlorine detection available, and CO2 reduction also very going well. And today I didn't explain detail, but some such kind of analysis also very near to the commercially available. So anyway, some of them can be realized. So I'm very happy. Anyway, finally, I'd like to say thank you to all of the co-workers in my group. This is Mita-san. Okay, and I want to say thank you, everybody. Okay, and finally, today I want to introduce our team in Indonesia in our group in Keio University. So far, we accept many Indonesian students. From 2010, this is my daughter, and Weni-san is the first student from Gajah University, and after that, so many students comes to 2013, 2014, 15, 16, 17, 18, and last year, some students came and back. Okay, and then finally I counted from the beginning to now. So I counted as 49 students from Indonesia. So especially this board student, not short time. Most of the students stayed 2 months, 3 months, sometimes 6 months or something. But these students stayed in our lab as a master student, and she stayed master and PhD. And he stayed master and PhD, and now Ilham is still now in our group, and he is now assistant professor in our group now. So he's working very hard. And Nita Sensei is now a PhD student. So I'm very happy. And not only that, Professor Ipandini in University of Indonesia, most of the students are her students. Actually, we had a very strong connection with her, and she stayed a long time in our group like this. And by her, she sent us many students, not only her students, but some other students from this university. So I'm very happy to enjoy with the Indonesian students. So you are always, we are always welcoming you. Okay, so thank you very much for your kind attention.
Okay, thank you very much for your nice presentation about boron doped diamond materials. So if I may conclude that this material has so wide applications such as environmental sensor, biomedical sensor, and also you focus on the improvement environment such as CO2 reduction. Also, it reaches good performance. So maybe moreover, this material is very promising in the future. Okay, we will talk deeply in the question and answer and discussion time. But now I will go to the next schedule. Thank you very much for your nice presentation, Professor Einaga.
Okay, thank you very much.
Hi, thank you very much. Once more, I repeat again our rules that the participants may do the raise hand in the discussion time. And second is the participants can give the questions in the chat menu along the speech and discussion time. And the third is the questions can be on Bahasa Indonesia. I will translate it in English to the speakers. So please, the participant, if you have some questions for Professor Einaga, please chat in the chat menu. We will discuss later. Okay. Thank you so much, Professor Einaga. He is also my supervisor here in my PhD candidate. Thank you for your support for us. Okay, next presentations will be held by Professor Tominaga. Before his speech, I will give explanation about his background. The committees, please perform the slides. Okay, this is the curriculum vitae of our second speaker. The complete name is Professor Dr. Masato Tominaga. I called him Professor Tominaga. And the formal educations from bachelor to master to PhD, he got from the Kumamoto University. And now the current position is full professor in Graduate School of Science and Engineering, Saga University. And he focused on the research interests on electron transfer reactions on biomolecules at electrode interfaces. About the grants, we got the Research Collaboration Foundation with Nishimo Electronics Industries Co. Ltd, Research Collaboration Foundation with Panasonic Co. Ltd, and also Sakura Science Program GST, and grant in aid for scientific research from the Ministry of Education, Culture, Sports, Science, and Technology, or MEX, Japanese government. Please welcome Professor Tominaga with the speech topic about characterization and application of carbon nanotube material. Time is yours.
Thank you very much. Thank you very much, Unita Sensei, for your my present introduction. So, this one. Can you see my slide? It's okay?
Okay. I can see your slide.
Okay. So, selamat siang, everybody. Nama saya Masato Tominaga, Saga University, Japan. First of all, I really appreciate all of this webinar committee member, especially Ms. Kusti Sensei and also Unita Sensei. I'm really honored to be here as a presenter of this international webinar, first seminar. Okay, I hope you remember name of Saga. So maybe you know Tokyo and Osaka and also Kyoto, but please remember Saga. I'm in Saga city here. So this is, please remember. So this is a very important point for me in this meeting. So maybe 6 months ago, I could visited Kalimantan, Balikpapan, ITK to make a MOU between ITK and the university. So before COVID-19, so we are lucky. I could visit Balikpapan. Okay, today's my topic is carbon nanotubes. So, of course, you know carbon nanotubes. So there are many types of carbon. So Einaga sensei introduced the diamond boron doped carbon nanotube. Also, some maybe you use graphite or some maybe graphene. So I use a carbon nanotube because the carbon nanotube has high electronic conductivity and also has a huge surface area in theoretically. Okay. So this is basic knowledge. So there are two types of carbon nanotubes. There are two types of single wall carbon nanotubes. Okay, metallic and semi-metallic single wall carbon nanotubes. Okay. So when you synthesize carbon nanotubes, you can obtain 33% of metallic carbon nanotubes, and the other 66% of semi-conductive one. Which one is depend on the chirality. So we can now we cannot control the chirality of a single wall carbon nanotube. So that this ratio is like this one. So this is the image of the electric density. So this is occupied electron occupied state. This is electron unoccupied state. So this state is bind each other. So this is metallic. So on the other hand, semiconductive one, these electron state is separated, not combined. So this is semiconductive one. So I have been used carbon nanotube for 20 years for electrode material. So today I would like to inform you very important point when you use the carbon nanotube for electrochemistry. Quality, contamination, and shape characteristics. The first one is quality. So you can buy carbon nanotube, still expensive, but the quality is quite different. Depends on the company. Maybe it depends on the lot. So this is Raman spectra of carbon nanotube. This is a multi-wall carbon nanotube. Nope. I'm sorry. Oh, sorry. Pointer. Yes. Multi-wall carbon nanotubes, a single-wall carbon nanotube. This is carbon nanotube I synthesized. So multi-wall carbon nanotubes has two large peaks. This is a D band. This is G band. Okay. So G band is due to the graphene seed. D band is due to the defect of sp2 carbon structure. So D band is high. It means this carbon nanotube has a lot of defect. So what kind of defect? Like this defect. The surface is oxidized. So oxidized functional groups appeared on the surface. So this is only single wall carbon nanotubes, but the quality is quite different. You can see this is the large D band. However, in this sample, you cannot see any D band. Okay. So this single wall carbon nanotube is very expensive. So you can check this like this quality. So you basically you can observe like this D band. So it means the lots of functional group. So the surface is hydrophilic. So you can easily disperse this carbon nanotube in the solution by using sonication. But in this case, there are no defect, so very hard to disperse in the solution. Also, other point is impurity. So when we synthesize carbon nanotubes, we must use metallic nanoparticles like this one. So this metallic nanoparticles is iron, copper, nickel, cobalt, something like that. Important point is this is electroactive metal. So many electrochemists try to remove these metallic nanoparticles by using acid treatment, strong acid treatment with sonication. Yes, we can remove the like these metallic nanoparticles, but surface, the carbon nanotube surface also oxidized like this one. This is just information. This is carbon black. D band is high. The glassy carbon, the carbon paper. So this is HOPG, so high oriented pyrotic graphite. This is very crystallized, so there is no defect. We cannot detect. Well, so sometimes this oxidized surface affect the enzyme reaction. This is principle no oxidized surface. When we use such a surface, we observe like this catalytic current of oxidation catalytic current of fructose dehydrogenase. It's an enzyme. So little bit surface is oxidized. This catalytic current is larger than before. However, surface very oxidized. This current is decreased like this. So also, electric structure of carbon nanotubes is affected by oxidation. So this is I calculated before. So this is the chirality 12, 0, single wall carbon nanotubes. And this is no oxidized state. So we can see a small gap here. So this means this is semiconductive single wall carbon nanotubes. However, 0.3% is oxidized, the surface. So this structure is changed like this. And 0.9% is changed like this one. So maybe you also care about like this one when you use the carbon nanotubes. So next is contamination. So there are 2 points. So I already mentioned the carbon nanotubes has metallic nanoparticles, and to remove these metallic nanoparticles, we use acid treatment and sonication. Yeah, after this process, graphene chip is generated. Like this graphene chip affect the some electrode reaction. So we synthesize carbon nanotubes directly on the electrode surface to remove such contamination and the to remove such problem. Okay, we use like this CVD equipment. This is electronic fluorescence. Closed chamber set in the this fluorescence, and we use ethanol as a carbon source, and we control the ethanol gas by using a mass flow, and then the electrode modified with the catalyst set in the closed chamber, and then we obtained carbon nanotubes. This is before carbon nanotube synthesis. This is after. The surface changed to black like this one. So this is a TEM image of the surface. So we can see many single wall carbon nanotube. Its diameter around 1 nanometer, the thickness around 20 micrometer. So recently, gold is very expensive. So we can use another metal, such as copper, iron, palladium, and nickel. This is also, we synthesize the carbon nanotube on the aluminum surface. So in our electrode, also we use the metallic nanoparticles, but these metallic nanoparticles are incorporated in the single carbon nanotubes. It means this metallic nanoparticle is not electroactive because this nanoparticle inside the carbon nanotubes. So we do not care about defect structure, metal nanoparticles, graphite impurities. And then we check the another, we investigate the contamination under the air atmosphere. So we use fresh carbon nanotubes. We can obtain very nice redox wave of cytochrome C. Cytochrome C is a biomolecule, redox protein. So we observed very nice redox wave of cytochrome C when we use a fresh carbon nanotube. However, the electrode is exposed to the atmosphere. This peak decreased quickly. So this is a peak current versus exposure time. So the peak current is decreased very quickly because this molecule is very sensitive to the surface. Also, this is ferricyanide. Ferricyanide also inhibited. Also, this reaction is inhibited by contamination. So when we use fresh carbon nanotubes, we observed nice redox wave of ferricyanide. However, 1 week later, the redox peak is inhibited. A redox reaction is inhibited like this one. Also, this is a ferrocene. Also, this reaction is inhibited. So you need to care about the contamination. So when you buy carbon nanotubes or another nanocarbon, the surface must be contaminated. So we cannot remove that contamination. When we use the more big solid carbon electrode, we can polish it, and we can make a new surface. But this is the nanoparticle, carbon cannot polish it. Okay, so to remove the contamination, we use another modifier. Okay, so this modifier can bind strongly with the carbon nanotubes or nanocarbon than contaminated molecules. So especially we use the sodium chloride. This is a very famous molecules reagent for the binding with the carbon nanotubes. This sodium chloride dispersed well single wall carbon nanotube in the solution. This is TEM image of the dispersed carbon nanotubes. You can see some carbon nanotubes. Also, this is a mixed solution, the carbon nanotubes and the kitchen plug. So also kitchen plug and the carbon nanotube is mixed well and dispersed well. And we check the catalytic current of lacase. But anyway, so when I use sodium chloride, the result is very repeatable. Okay, this single wall carbon nanotube obtained from a company. The third topic, shape characteristics. Okay, carbon nanotube is very small size. Okay, and one-dimensional shape. Okay, this diameter is almost same to the diameter of a molecule of reactor. So this is a cyclic protonogram of NADH. At NADH is a biomolecules at various electrode. Okay, and, HOPG and plastic formed carbon, the glassy carbon. The important point is this is our carbon nanotubes. Important point is carbon nanotube and HOPG is also sp2 carbon. HOPG is no defect, very flat surface. So at the this single wall carbon nanotube surface, we observed the oxidation reaction started from 0 volt, right? On the other hand, at the HOPG, this reaction started from around 0.3 volt, quite different. This is in the case of beta carotene. This is so we use many types of electrode, platinum, glassy carbon, HOPG, and the single wall carbon nanotubes. So HOPG, in the case of HOPG, the cyclic volothermogram is like this one, but in the case of single wall carbon nanotubes, like this one. So I analyzed this reaction. In the case of the HOPG, the beta carotene reaction is diffusion controlled reaction. However, in the case of a single wall carbon nanotubes, this reaction is adsorption species.
I'm sorry, Sensei.
Yeah, time is limited.
Will be over. So maybe you can make it shorter. Sorry, I'm sorry.
Okay. And we can cut off the cap of single wall carbon nanotubes by control the potential. So when we selected the potential, we cut off the cap, and we can beta carotene can incorporate in the inside of a single wall carbon nanotubes. Okay, I prepared the cellulose nanofiber. I'm sorry. I prepared the composite film of cellulose nanofiber and the multi-wall carbon nanotubes. I prepared like this film. Okay, so multi-wall carbon nanotube is incorporated in the inside of a fiber of a cellulose nanofiber. And I prepared like this enzymatic biofuel cell. Okay, this is my message to you. And then this is acknowledgement. And I invited many Indonesian teachers and students. So after COVID-19, I will continue to invite teachers and students to my lab. So now I'm preparing my homepage in Bahasa Indonesia. So that is coming soon. So if you interested in my research, please invite my homepage. Terima kasih. Thank you very much.
Okay, thank you so much for your interesting lecture about single-wall carbon nanotube materials. I can get from your information here that we must careful about the contamination of carbon nanotube. Then it's very good reminder for us that you found in your research that there is contamination in carbon nanotube. So maybe we can consider the modified to maintain this contamination. Okay, we will discuss later deeply about this in the question and answer sessions. Thank you so much for your nice presentations. Thank you. Thank you, Professor Tominaga. Once again, I remind you, ladies and gentlemen, you can give the questions in the chat menu along the speech and discussion time to the host. So the message only you can send to the host. Please provide your questions, and the question can be on Bahasa Indonesia. So I will translate it in English to the speakers. Okay. The last but not least, we have our third speaker here, Dr. Nofrijon Sofyan. I will let you know about his background. The committees, please perform the slides. Okay, this is the curriculum vitae of our third speaker. Complete name is Nofrijon Sofyan, PhD. And he got the bachelor degree on the Universitas Andalas and the master degree in Universitas Indonesia. and the PhD degree in Auburn University. The current position of him is Associate Chair, Department of Metallurgy and Materials Engineering, Universitas Indonesia, member, the National Research Council for Advanced Materials. And about the research interest, he focused on the nanostructured materials for new and renewable energy, especially for battery and solar cell energy. And the awards, the latest award is in 2020. He comes in the best 500 researchers in Indonesia. This is a very good awards in the lately 2020. Okay, it's time to see his lectures about characterization of nanostructured materials for renewable energies application. Dr. Nofrijon, this time is yours. Please.
Thank you very much for nice presentation, moderator. Can you see my presentation?
Yes, I can see clearly. Maybe you can show the, okay.
Okay. So firstly, I would like to thank the committee for inviting me in this first international webinar series. I am very honored. My today's topic is about characterization of nanostructured materials for renewable energy applications. But my talk, I think, would be more general as compared to Professor Einaga and Professor Tominaga. Before that, I am Nofrijon Sofian. So again, as has been mentioned before, I am Associate Chair at the Department of Metallurgical and Materials Engineering, Universitas Indonesia. Before going further with the presentation, I would like to show you a little bit about our university and Metallurgical and Materials Engineering Department at Faculty of Engineering, Universitas of Indonesia. A very short video.
Welcome to Faculty of Engineering, Universitas Indonesia. We are Indonesia's top public engineering institution with global reputation. Established in Federal of Republic of Indonesia, Faculty of Engineering Universitas Indonesia has become an important part in the history of nation building.
Sorry, Dr. Nofrijon, we cannot hear the voice of your video.
Okay, but you can hear my voice?
Yes, I can hear your voice. Or this video has no voice?
Okay, it should have a voice. But maybe this is only a short video. Yeah, it will be finished soon.
Okay.
Okay, so sorry if you cannot hear your the sound of the video, but it doesn't matter. So I just want to show you our student body at Metallurgical and Materials Engineering, Universitas of Indonesia. Actually, we have several programs at Metallurgical and Materials Engineering. We have around 700 students for undergrad and graduate students. For the undergrad, we have a regular parallel international program, and we have master's and PhD students. The numbers is here. For the international students, we have a collaboration with a dual degree with Monash University, University of Queensland, Curtin University in Australia, And also we have dual degree programs with University of Duisburg Essen in Germany. And hopefully with this collaboration, yeah, actually we do hope, we don't have any collaboration dual degree with the Japanese university yet. Yeah, hopefully, I don't know if maybe Professor Einaga and Tominaga could bridge this collaboration in the future, hopefully. And now back to our presentation. My topics is about renewable energy materials. So maybe the question would be, what is renewable energy materials? So in brief, yeah, we can define a renewable energy as a kind of energy that cannot be depleted when used. So different from coal or maybe oil that have limited deposit. As the name implies, this renewable energy can be renewed if we take care of it properly. We may think about maybe biofuel from plantation. We may think about wind energy. Yeah. We may think about solar from the sun. Yeah. The huge energy source in our universe. And we could also think about geothermal energy. As you may know, some parts of Indonesia are located at the rings of fire. That way, we have many resources for this geothermal energy. We could also think about ocean. So 80% of our country is ocean. We could also think about hydropower and so on. And all of these technology are available. Yeah, but for this today's presentation, I would like to narrow it down to solar energy in the form of a solar cell and solar energy storage for this solar cell. Talking about the solar cell, yeah, the basic technology, yeah, actually has been quite a while, yeah, starting from the first generation of silicon-based solar cell, and the second generation of thin film solar cell, and the third generation dye-sensitized solar cell, and the latest one, perovskite solar cell. All of those technologies actually are based on photovoltaic effect. So when we think about photon, for example, the energy from the sun, yeah, absorbed and used in a specific way, so we could generate electricity. Or in this instance, we arrange electron flow to become an electrical and to become an electricity. So I'm talking about the third generation and the fourth generation. I'm not talking about the first and the second generation, but this third generation, what we call as a dye-sensitized solar cell, working basically based on which photosynthesis works. So we use a dye as a sensitizer for a specific semiconductor. So for example, we use titanium dioxide or maybe zinc oxide for the semiconductor. So when the energy from the sun, for example, yeah, strike the sensitizer, so the electron will excite it, and then going into a band gap of the semiconductor. And that way, the electron flow result in a specific generating of the electricity. And the second one, what we call the perovskite solar cell, basically the fourth generation of the solar cell. So in this perovskite solar cell, the main compound come from the perovskite structured materials. So in this instance, the active layer is conducted with what we call as an N-type semiconductor, and then P-type material for hole extraction. So here we have a perovskite structure, a metal ammonium iodide or maybe chloride, and then we have N-type zinc oxide, and we have a spiral method for the P extraction, a P-type extraction. The big challenge in these materials is how to synthesize the materials, and of course, how we characterize the materials. In this instance, in the term of semiconductors. So we could synthesize nanoparticle, or maybe nanorod, nanoflowers, and etc. And also because in the dye-sensitized solar cell, we need two electrodes, the anode and the cathode, in the form of counter electrode. So usually for the better one, people usually use a platinum-based material, and of course this is gonna be expensive. So the choice gonna be maybe carbon-based materials here. So we could also think about carbon-based materials from the natural resources. And the other things is we could also develop the subset materials, for example, transparent conductive oxide, in the form of fluorine-doped tin oxide, or maybe indium-doped tin oxide. And also, of course, for the dyes, both for the synthetic and the natural. And in addition to this technology, because as you know, when we have solar cell, we could not have energy during the night. So we need to store the energy. So how we can store the energy? Nothing but to develop a battery. So for this battery, lithium-ion battery appears as a solution to the high energy density requirement. And especially because of the with the advancements of the technology, the life cycle and the working voltage is getting increased. So I have actually a lot of stuff to show you, but I think I just skipped some of them because we don't have much time to show you. But again, the challenge in the material development is how we could synthesize it and how we can characterize it, as has been implied in the title, how we characterization for this renewable energy. So this is just some of the that we work in the lab. The first generation lithium cobaltate, lithium manganate phosphate, and lithium ferrophosphate. But each of these materials has its own advantages, and of course, their own disadvantages. For example, here, lithium cobaltate, it has a high energy, but kind of toxicity from the cobalt, for example. Lithium manganese phosphate, for example, it has a high working voltage, but it has short life cycle. And for the lithium ferrophosphate, we have a lower working voltage, but we have much longer life cycle. So because of that, we need to compromise between these materials. So how we can synthesize better materials with better performance and of course with a better life cycle. So again, in addition to that, the development of those materials, of course we need a good material. So far, what we do is buying the materials from abroad or import the materials. And of course, actually, Indonesia is rich with these kind of materials. For example, one in Bangka Islands, we have, as you may know, we have tin mining right there. And in addition to the tin mining, we have a byproduct, what we call as ilmenite. This ilmenite contains the one that we use for the solar cell development, titanium dioxide. So how we can get this material from this local mineral. So the challenge would gonna be how we can extract it and how we can use it for better performance of the solar cell. So we do synthesize from the purified mineral that we took from our local mineral. So we synthesize here. We start with the titanium dioxide nanoparticles. So by using the known method for reflux, for example, and hydrothermal, we synthesize a nanoparticle. Titanium dioxide nanoparticle, and we characterize it using this X-ray diffraction. We compare the peak that we obtain from our synthesis and the one from the commercial one. From this one from the commercial one, the B. A is a reference, and C, D, and E. This is different method that we apply. So we can see that our synthesis result in a single phase of anatase. Actually, this is anatase titanium dioxide. This is actually that we need. So we continue with the field emission electron microscope. We see a nice particle, nanoparticle, grown very, very nice. And then we further characterize it using a transmission electron microscope. As we can see here, very, very nice, smaller than 50 nanometers, as you can see here. Maybe this is around 20, maybe up to 40 nanometers. And we also do some high resolution transmission electron microscope, as you can see here. Nice orientation of the crystal structure. And this is selected area diffraction of the TEM, showing a single phase of the anatase. This is another material that we develop in our lab. We call it as a nanorosette. Some people may call it as a nanoflowers, but here in our lab we call it as a nanorosette, a titanium dioxide. So here we also do some characterization, X-ray diffraction, some transmission electron microscope, high resolution transmission electron microscope, and some of the selected area diffraction. And we could also propose some mechanism for the nanorosette formation. And this is also, this is another work in our lab, how to develop a nanotube. In our lab, we do some different synthesis, different method. We could also obtain with this one, very, very nice nanotube. Some characterization, again, using X-ray diffraction. Some transmission electron microscope. This is STRI-TiO2 titanium dioxide nanotubes. And again, I think I might skip some of the result. We can come back later if you need to ask it. Okay. This is different we call it as a post hydrothermal treatment. A different treatment. At 150 centigrade, and this is about 300 centigrade. We obtain very, very smooth nanotube crystal anatase. This is some work on the zinc oxide. This is actually just, this is for the perovskite solar cell, basically. We grow zinc oxide nanotube, very, very nice ground on the substrate. This is some characterization. But in addition to that, when we talk about, again, as I mentioned before, we need dyes for the dye sensitized solar cell. So we have the option to use chemical-based dyes, or we can have environmentally friendly materials that we can obtain from our local resources. So for example, here, we've tried different dyes, from, this is from pitaya, dragon fruit, from strawberry, from mangosteen, pericarp, and this is this one. This is actually we call it as a weed in the plantation, actually unwanted. But if we can obtain the seed from this plantation, we could have very nice black dyes that could be used in the dye sensitized solar cell. So this is just to show you some result of the dyes extraction. Okay, and the other things, we use carbon from natural resources. As mentioned before, dye-sensitized solar cell use 2 electrodes, anode and cathode. The one from the cathode we usually use for the better one, platinum. But here we obtain a natural graphite. So here we use coconut shell, rice husk, and bamboo, in which we obtain charcoal, and then we convert the charcoal into activated carbon and then to graphite. And basically, from graphite, we could also transform it into graphene and or maybe carbon nanotube. Okay. This is some result of the dyes characterization, infrared. This is a combination of the dyes and a semiconductor. And this is the semiconductor that we synthesize ourselves in our lab. Okay. And this is the extraction using different solvent. Okay. And this is from the UV phase, ultraviolet visible for the absorption also, just like before. This is band gap calculation. I'll skip it maybe. Okay, this is some thermal analysis. This is just to show you the solar cell fabrication. Okay, the standard day, the dye variation from our harvesting dyes from the local resources. Performance testing, we use direct testing, and the one using lab testing using semiconductor parameter analyzer. Okay, so we good means quite a good result from this one. Okay. This is some electrochemical work, using electrochemical impedance spectroscopy. So this is actually Nike's plot. This is a board plot, magnification of the board. And this is performance, using semiconductor parameter analyzer. Okay. Just like before, this is for the battery, the prefusion from the for the solar cell. We also do some synthesis for the active material for the battery, lithium-based batteries. Okay, so this is some result that I'd like to show you. This is a field emission electron microscope. This is X-ray diffraction. We obtained quite nice. This is for the references. A reference, and this is the one that we synthesize in our lab. And this is I try to obtain elemental mapping of these materials, and we see even we still need to improve some. The distribution of the materials is quite nice. Okay. So we also do some battery fabrication and testing. Again, different depends on what kind of batteries that we would like to develop. Here, because we only obtain small amount of active material, so we just select in the form of battery coin, and we try to check for the Nike's plot and the cycle voltammetry. Actually, we have also the this chart and this chart, but I think I just forgot to put it here. Now for the summary for our characterization, we need X-ray diffraction, actually for the crystal structure, UV phase for the infrared UV phase and infrared for the absorption, thermal analysis for the thermal stability, electron microscope, both scanning and transmission, yeah, especially for the morphology, and for the especially for the selected area fraction, yeah, to support the one that we got from the X-ray diffraction. And also for the elemental mapping, we need energy dispersive X-ray spectroscopy, semiconductor parameter analyzer, and of course the electrochemical impedance spectroscopy. And the other thing that I didn't put here is a neutron source, yeah, for the lightweight element, yeah, because for the lithium, this is we cannot detect it using X-ray diffraction. This is some of the papers that we published from our lab, yeah, and this is our members. And again, thank you very much.
Okay, thank you for your nice presentations about nanostructures materials. From your explanation that I got some informations, you explore more the materials for solar cell and material for battery to improve the energy, to improvement the energy of battery. And also you explore the natural resources for dye. It's very good. As we know, Indonesia has so many natural resources.
Yeah,
okay,
we are rich actually.
Maybe next we can discuss in the discussion. Okay, again and again, I remind you to give the questions. You can give the questions via chat menu along the discussion time, along our discussion time. And the question can be on Bahasa Indonesia. I will translate it to the speakers. And now, you can fill the absent to get the e-certificate. So without the absent, you cannot get the e-certificate. So please click the link that the committee give you in the chat. And now we go to the next session of discussion by raise hand menu. First, I will open a chance for participants to take raise hand and ask questions and discussion directly to our speakers. After the question from the participant, the speaker can answer directly. So this time is the question for Professor Einaga. To remind you that Professor Einaga explained about electrochemical application for boron doped diamond material. Please, you can use raise hand menu. The committee, maybe you can give. Committee, please. Who will be? Okay. Okay, hello. Can you hear my voice? Okay, thank you for moderator for the time. Maybe I would like to introduce myself first. My name is Kartika Anuraga Madurani, and I'm a doctoral student right now in chemistry department in ITS Surabaya, Indonesia. So maybe for the firstly, I would like to say hello first for all speakers today, for Professor Einaga, Professor Masato Tominaga, and Mr. Nofrijon from, sorry. Okay, I will start my video. For all speakers, it is very nice presentation. Learn more about carbon materials today. So it is very excited for me today. Especially for Professor Masato Tominaga, maybe konnichiwa sensei. It is nice to meet you in your webinar today, and I hope we can continue our collaboration next after this pandemic. So, okay, actually, I also work in carbon material, especially in graphene for sensor also, but I also interest with Professor Einaga presentation. So I would like to question for him. I have two questions. For the first is how about the durability time, the sensor materials? And the second question is it possible if we want to produce the sensor based on BDD material in industrial scale? Because as far as I know, diamond is not a cheap material, I see. And so I want to learn more about BDD material from Professor Einaga. Thank you so much.
Okay, please, Professor Einaga, you can explain. Maybe the first question is about the reliability.
Okay.
Right? Hi.
Okay, thank you. Thank you for the question. Thank you very much. So first about durability, I think the diamond is a very, very stable material, as you know. So this is the most important advantage point of the diamond material. So durability is always almost perfect. I mean, there's many, after many times operation, still the bond of diamond is active. So one negative point is for wastewater treatment application. You know, when the wastewater treatment application is also very interesting topic. By using bond of diamond, OH radical, a hydroxide radical is generated on the surface. So the organic compound can be decomposed very easily by using bond of diamond. But after using long time by applying the high potential, like 3 volt, 4 volt, or something like that, and using the organic compound, at that time the surface of the diamond is gradually shows a corrosion, so becoming bad. So only the wastewater treatment application we should care about the durability. But sensor application, CO2 reduction application, almost okay, very, very stable. So sensor is okay. So this is okay for your question. And how about second question, Anaki?
Okay, Sensei. The second question is about how if it is production, big production, because diamond is expensive, as we know.
This is a very, very good question. Thank you very much. So, as I told you, the history of the bond of diamond is very limited. So we started from our lab, and this is the original one. And actually, gradually, many companies are interested in bond of diamond. So I push many companies to make BDD cheaper. And so now several companies, we collaborate with such company for the diamond production company, are interested in making bond of diamond for sensor application, CO2 reduction application, and they are trying to reduce the price to cheap. So I hope in the near future, several years later, I think we can buy cheap bond of diamond easily. I hope. I want to push Indonesian company also to make BDD cheaper. Anyway, this is how to say, we have a future plan to use very easily for you also. Thank you very much. Is it okay?
Is it clear for you, Miss Kartika?
Okay. It's very clear. Thank you so much, Professor Einaga. Thank you.
Thank you.
Okay, thank you so much for your questions, Ms. Kartika. Now, the next is the time for the question of Professor Tominaga. For participants, you can use raise hand menu, please. Anybody? The committee, please. Anybody? Oh, okay.
Hello.
Oh, okay. We select Mr. Tripaus Hasiholan, Tripaus Hasiholan Utapia, University from University
Okay.
Borneo Tarakan. Please perform your questions.
Thank you. Hello, my name is Tripaus Sasiolan Hutapea from University of Borneo Tarakan, North Borneo. Okay. Hello, Professor Tominaga. How are you?
Hello. Fine. Thank you very much.
We cannot hear your voice clearly.
Hello. Yeah.
Oh,
You
like
can hear me? Hello.
Okay.
Hello. Hello.
Hello.
Hello.
Okay.
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 Yeah. Okay. Okay. Hello, Professor Tominaga. If you remember, we met few times at ITS Surabaya.
Yeah, I remember.
Nice to meet you again online. Yes.
Yeah.
Thank you for your nice presentation about carbon nanotube. My question is, how is the carbon nanotube perspective in the future, and can the nanotube fabrication be made from natural resources? Thank you very much for your attention.
Okay. Okay. Thank you very much. Nice question. I'm okay. Okay. Thank you very much. Nice question. Of course, I remember you. When I visited Surabaya, I met you at the front of hotel, right? So about your question, so carbon nanotube is still expensive. It's a problem. So everybody focus on the graphene or graphene oxide because it's much cheaper than carbon nanotubes. That is the problem. So we need to focus on some special using or we need to use carbon nanotube some special using for some special detection, something like that. So also sometimes carbon nanotube is not good for our health. That's why it's also problem. Okay, multi-wall carbon nanotube is not so bad, but single wall carbon nanotube is no good. So that we need to resolve that problem to use wider in the world, I think. So I'm sorry, my answer is not clear, but is it okay for you?
Okay. Is the answer clear for you, Mr. Tripaus? Hello? Oh, okay.
Yeah. Thank you, Professor Tominaga.
Yeah.
Okay, thank you very much for your enthusiastic to give the questions.
Also, I want to say additional information. So
Okay.
carbon nanotube is single wall carbon nanotube is very nice material for studying principles, studying fundamental research. Very nice material. Thank you very much.
Okay, thank you very much, Tominaga, for your answer. So now the question is for Dr. Nofrijon. For participants, you can raise hand in the raise hand menu, please. The committees who will be selected.
Okay.
Okay. We select Mr. Hiskia Alpa to speak about your questions, please.
Okay, thank you very much. Thank you very much, Miss Yunita Triana and Professor Einaga, Professor Tominaga, and Dr. Nofrijon Sofyan for your presentation. My first question is for Professor Einaga. Yes, konnichiwa, Professor. I want to ask about the biocompatibility of diamond sensor inside human body, since we know that another micro or nanoparticles like asbestos or carbon nanotube having some proven or disputed bad effect in human body. How about the effect of nanodiamond or microdiamond in human body, especially for sensor application? And the second question is for Dr. Nofri.
Yeah, actually, this time is question for Dr. Nofrijon, Mr. Hiskia Alpa. Maybe.
Oh, Nofrijon. Oh yes, I'm sorry. I'm sorry. I'm sorry. This is for Mr. Nofrijon. This one, I asked about, especially about the titanium extraction. We know that in other countries, like in Malaysia, our neighbor, there is some problem in extraction of minerals, especially rare earths and lithium and some kinds of that, because the fear of radioactive waste, side waste caused by the mining process. What I want to ask for you, in the production of titanium from ilmenite, is there any risk of such dangerous minerals that could be produced, or I mean waste, not minerals? And the second one, we know that the SCC is one of the promising type of solar cell, but we also know that some of other types like the classic graphite and silicons have bigger efficiency, stronger efficiency than the SCC. How we could improve the SCC, and actually what is the strong points of developing the SCC compared to classic solar cell like silicon or like graphene type of solar cell? Thank you very much.
Thank you for your questions. So please, Dr. Nofrijon, time is yours to.
Okay, thank you very much for the question. The first question about radioactive effects on the, if we, for example, if we take the materials from the mining, that's maybe the question. Yeah, there is a rule for that. Yeah, we cannot just go there and take the materials. No. Yeah, in Indonesia is under Bapeten, yeah, Badan if I'm not mistaken, that's the Council for the Radioactive Materials. Yeah, so there's a rule. Yeah, but as long as we mentioned about the ilmenite. So as long as we don't have a radioactive material, it should be okay. Yeah. So we need to work with the proper and caution for the materials. Yeah. Because some of the rare earth that obtained from the banca, it contains some radioactive. Yeah. But again, we need cautious for that. And the second question about the DSSC, compared to the silicon base, still actually much lower. Yeah, I think the best metal, single crystalline metals, is around 24%. Yeah, and I think for the DSSC, it's only about 14%. Yeah, and for the one that use natural resources, I think our best achievement is just around 5%. So it's much lower. But compared to the difficulties, in fabrication, for example, for the silicon base, we need a deposition. That's very expensive compared to the DSSC. For the DSSC, we can just create it in our lab. It's very simple. So we have to compromise between difficulties and the easiness, and the expensive and cheap materials. I think if that answers your question.
Yes, I think. Yes, thank you very much, Dr. Nofrijon Sofian, for your answer.
Okay, thank you very much for your participation, Mr. Hiskia. As the information, Mr. Hiskia Alpha is one of our lecturer in Material and Metallurgical Engineering ITK, Dr. Nofrijon.
It's very nice. Yeah, thank you very much.
Thank you. And now we enter the last session in question and answer from the participants. In the chat menu, we already gathered the questions from the participants. I will open the first round, that one person for one speaker. Then if we still have time, the second round will be continued. First, it is for Professor Einaga. Okay, the question is from Andromeda. Now, Mr. Andromeda is one of the lecturer in our department also, ITK. This is question from Professor Einaga. Your research is really interesting. There are many research about BDD from you. One of your research application is semiconductors is for the medical field using BDD. And the method is using electrochemical analysis experiments. The question is, how is the application of BDD research in the industrial sector? Are there any obstacles? Second question is, why not use silicon doped diamond for your research? Silicon has good conductivity when doped with diamond, and it's easier to find compared to boron. Maybe that's all. Time is yours to answer, Professor Einaga, please.
Okay, so first question is, I forget first.
How is the application of BDD research in the industrial sector?
Okay. So yes, as I mentioned in my talk, the sensor application for environmental sensors such as heavy metal like arsenic or such kind of one is now almost commercially available. And then, as I mentioned, chlorine sensor is recently very popular. I mean, everybody need the detection of chlorine due to the COVID program, so for the disinfection. So this is really almost commercially available now in Japan. So from now, I want to advertise such a property to the worldwide to use. In China recently, some, for example, the cadmium detection in rice is also started to commercially available. But except the sensor application, some applications are commercially available, but still in progress. For example, CO2 reduction will be very new trend in the world. So in the near future, this will be very big market. Is it okay? So the second question is,
Please unmute. Unmute Unita, yes.
Why not use silicon doped diamond for your research?
Silicon doped diamond, silicon doped diamond. So, you know, the boron is, how to say, boron doped silicon can be a p-type semiconductor. This is well known. So the, for example, the phosphorus can be a negative N-type semiconductor. So the carbon and silicon and boron can be a partner for the p-type semiconductor. So boron and carbon is also same. The one hole generate. You know, the electron number is one electron is different between carbon and boron. So this is the origin of the conductivity. The hole can be a carrier of the electron, you know, for the conductivity. So this is the reason. So silicon doped carbon is very, I don't know how is theoretical opinion is, I'm not sure. So boron is important for the doping compound. Is it okay?
Okay. Okay, maybe it's clear answer, Sensei. Thank you very much for your answer. And we go to the second questions. It is for Professor Tominaga. The question is from Aulia Fajrin, STMSC. She is one lecturer in Polytechnic Negeri Batam in Sumatra. He asked to Professor Tominaga, the question is, would you like to explain more about spray pyrolysis that relates to carbon nanotube as hydrogen storage? I repeat again. Would you like to explain more about spray pyrolysis that relates to carbon nanotube as hydrogen storage?
Hydrogen storage?
Yes.
Hydrogen storage. So which slide? Hydrogen storage? No.
Hydrogen storage, Sensei. To storage the gas hydrogen, H2 storage. Yeah, would you like to explain more about spray pyrolysis that relates to carbon nanotube as hydrogen storage?
Hydrogen storage. I understand. Okay, okay. Yes, yes. Maybe more than 5 years ago, many researchers focus on the research using carbon nanotube for hydrogen storage. But recently, I do not see any paper. So maybe I think the durability is a problem, I think.
Okay.
So hydrogen is a very, dangerous gas. So that is my answer. It is possible.
It's not good for the hydrogen storage, right?
Yes.
Sensei? Because the durability. Okay. Okay. Thank you for your answer. And the third question is for Dr. Nofrijon. It is from Bodi Gunawan, Mr. Bodi Gunawan, but he is not right the institution. First question is, which one of TiO2 materials is the best for solar system? Anatase, nanoroset, nanotube. And the second, could you explain briefly how to fabricate charcoal into graphite? Time is yours, Dr. Nofrijon.
Okay, thank you very much for the question. Which one better, anatase, rutile, or maybe
nanotube?
nanotube. Yeah, actually there are for the DSSC there are several. It depends on the process how you create the solar cell. Yeah, in our lab usually we use Anatas one. Yeah, for the DSSC, but other researchers have created a mix between rutile and Anatas. So it depends again. Depends on your process. For the charcoal, yeah, how you can create graphite from biomass. So basically, you do the pyrolysis method. So I think you could Google pyrolysis and you could find it. Yeah, and then actually. If you also do some treatment, yeah, you could get activated carbon first and then into graphite. And then by using hammer method, you could transform graphite into graphene. Yeah. So I think you could Google it.
Okay. How about the second?
That's the second question. Charcoal.
Charcoal into graphite.
Yes.
That's the answer. Okay, thank you very much, Dr. Nofrijon, for your answer. Okay, I would like to open the second round because still so many questions from the participants. Thank you for all your participate today. But Ma, we are so much honored of your interesting in this discussion time. Unfortunately, we are limited by the time. Sorry, I'm so sorry. That maybe you can give questions to the email of our email, mma@itk.ac.id, and we will request to the speakers to answer your questions. Okay, before I give back to Ms. Gusti in this discussion time, I would like to give some conclusion of today's material. First is boron doped diamond, carbon nanotube, and nanostructured materials can be applied in sensors and renewable energy which show good performance. And second, the materials development is very promising in the future based on the characteristic and many applications for that. And the third is the most important point, more studies are needed to improve the reliability of the material in many applications. So maybe it can give some inspiration today for us to continue this material, the research of this material. Okay. For the speakers, Professor Einaga, Professor Tominaga, and Dr. Nofrijon, thank you for your time and support for us today. Thank you
very much.
Information about the recent materials. It gives us many inspirations and knowledge in our discussion time. See you on the next event in the future. I give this time back to Ms. Gusti. I'm sorry if there are some weaknesses from me to hold our discussion time of this international webinar. Wassalamualaikum warahmatullahi wabarakatuh. Have a good day, everyone.
Bye-bye.
Thank you very much.
Thank you very much.
Thank you very much for the speakers. Thank you very much, Sensei.
Thank you for the amazing speech from the speakers and lively discussion from the participants. Thank you also, I have to say, to our beloved moderator, Universitas MSE, for leading the session perfectly. I want to remind you all to fill out the attendance that our committee provide in the chat box. I also especially want to appreciate Professor Dr. Yasuaki Einaga, Professor Dr. Masato Tominaga, and Dr. Sofia Nofrijon, who are warmly accepted our invitation. I am extremely excited to collaborate with amazing speakers like you. I am being honored. Thank you very much. Also, many thanks to our rector, vice rectors, head of faculty, head of department, and the committees who strongly supported our event until it is happened. Thank you for all the participants who come to the international webinar. If you need more information or question about the webinar, you could contact Ade. The mobile phone number are shown in the chat box. As mentioned before, if you have questions for the speakers, you could send us email to mme@itk@ac.id. Finally, we are in the end of the webinar. Hopefully, this event could give you inspiration and new insight about the recent technology on material science and engineering. We apologize if there are any mistakes from the committee. We need your feedback to improve our quality of event. Hope you have a great day. See you on the next webinar.
Rara 先生のくさび。あ、ミュートですよ。
Okay.
Go out.
That's okay. Thank you.
Thank you.
Thank you.
永先生。日本語でちょっと質問していいですか？
はい、何でしょうか。
ドロープのダイヤモンドはプラズマを使われてたじゃないですか。
そうですね。
あれ CVD とかあんなふうなやつはダメなんですか？